Now we will try factoring polynomials. In general, factoring means that we are taking a number or an expression and we are writing it as a product of smaller numbers or smaller expressions. For example, when we have 18, we can write it as 2 times 9, or -6 we can write as -2 times 3. We can factor polynomials exactly as we do numbers. We measure the size of a polynomial by the degree. Whatever the largest power is among all of its terms. That's how we will decide that a product is really a factorization. It becomes smaller by a degree. The property that we will use to actually obtain these factorizations is the distributive property. For real numbers a, b, and c, we have a times b plus a times c is equal to a times the quantity, b plus c. We can use this to factor out common terms from an expression. Suppose that we want to factor 2x plus 6. We notice that 2 is a factor of 2x, but 2 is also a factor of 6. So we can write 6 as 2 times 3. Now using the distributive property, we can pull that 2 out to the outside, and we are left with 2 times the quantity, x plus 3. So let's start with really factoring the simplest kinds of polynomials. We'll factor a monomial. Monomial being just x to the n, having one single term. So remember that for a factorization, we need to have the powers of the factors be smaller than n. So let's say that we wanted to write all of the factors of x to the 5th. So the real trick to make this work is that the exponents in the factors must sum to 5. Now, what property of exponents is actually being used there? Okay, so x to the 5th, we can write as x to the 4th times x to the 3rd times x squared, x to the 3rd times x, x to the 5th times x squared times x. We can write x to the 5th as x squared times x times x times x, or we can write x to the 5th as x times x times x times x times x, a total of 5 times. Now in each one of these factorizations, notice that the degree on each factor is smaller than 5. And that's exactly what we mean by having a factorization. Now a little problem for you to try. Suppose we want to find all of the factors of x to the 6th power. Here's a little hint. Once you write them all out, there should be 10 of them. So now, what's the greatest common factor of two polynomials? The greatest common factor of two polynomials is the largest polynomial expression, which is a factor of both polynomials. So recall that to find the GCF, one approach is to factor into a product of primes. This is exactly what we need. This is the importance of primes. Primes cannot hide any other factors. The primes are the fundamental elements. They are the atoms. We can't factor them any further. So those are our basic atoms. Those are our building blocks that we use to build all other numbers or all other polynomials. Before turning to polynomials, let's try finding the GCF of two numbers. The primes in the GCF will be the primes which are common to both prime factorizations of a and b. The exponent of the prime which appears in the GCF will be the smallest of the exponents for that prime in the factorization of a or b. So for example, let's suppose that we want to find the GCF of 490 and 686. If we factor each number into a product of primes, this is going to give us 490 as 2 times 5 times 7 squared, and 686 as 2 times 7 squared. What primes are common to each one of these? Well, we've got a 2 which is common and a 7 which is common. The smallest power of the two, which appears in either factorization, we only have a 2 to the first and a 2 to the first, so the smallest power is 1. So we have a 2 to the first power in our factorization of our GCF. The smallest power of 7, which appears in either factorization, is 2. We have 7 squared in 490 and 7 cubed in 686. So the most number of 7s that we can take and still be able to divide both of them is 2. So we have 7 squared in our factorization of our GCF. So 2 times 7 squared is 98. Actually, finding the GCF of two monomials is really easier than finding the GCF of numbers. This is easier because factors can't really hide in the monomials as they do with the regular numbers. The variable is the prime, and the smallest power of the variable which appears in the expression is the power of the variable in the GCF. So if we wanted to find the GCF of x cubed and x to the fifth, that is just going to end up being x cubed, because x cubed divides x cubed, obviously, and x cubed will divide x to the fifth. If we take x cubed times x squared, we get x to the fifth. So the GCF is x cubed. What if we have multiple variables in our monomial? We still only have one term, but we've got maybe an x and a y. In this case, each variable is acting like its own prime. X acts like a prime and y acts like a prime. The smallest power of x, which appears in the factorization, is 4. We've got an x to the fourth here. We've got an x to the seventh here. So the smallest power which appears in our GCF is x to the fourth. The smallest power of y, which appears in either factorization, is 3. We have a y cubed. We have a y to the eighth. So the smallest power of y we can have in our factorization, in our GCF, is y cubed. Okay, and if we want to see that x to the fourth times y cubed is a factor of x to the seventh y cubed, we can write x to the seventh y cubed as x to the fourth times y cubed times x cubed. If we want to write x to the fourth times y to the eighth as a factorization using this, we've got x to the fourth times y cubed times a y to the fifth. If we add the exponents on the y's, we get y to the eighth. So sure enough, x to the fourth y cubed is the GCF. Now when we want to factor a monomial from a polynomial, we really want to find the GCF for each of the terms in the polynomial and then use the distributive property. So if we want to factor the GCF from the polynomial 24y minus 6y squared, we need to find the GCF of 24y and 6y squared. Well, the GCF for the coefficients, we've got a coefficient of 24, which factors as 2 to the third times 3, and 6, which is 2 times 3. So the GCF of 6 and 24 is 2 times 3, or 6. Likewise, if we've got the smallest power on the variables which appear, well, the smallest power on the variable y is 1. So if we want to find the GCF of 24y, 6y squared, it is 6 times y. So factoring each one of those terms, we've got 24y is equal to 6y times 4, and 6y squared is equal to 6y times y. So using the distributive property, our 24y minus 6y squared looks like 6y times 4 minus 6y times y. Using the distributive property, we can pull out the 6y, leaving us with 6y times the quantity y minus 4. As another example, suppose we want to factor the GCF from 9a to the fourth minus 6a cubed plus 3ab. We find that the GCF of 6a to the fourth, 6a cubed, and 3ab. Well, let's look at the prime factorizations of those. 9a to the fourth is going to factor as 3 squared times a to the fourth. 6a cubed factors as 2 times 3a squared. 3ab factors as 3ab. So the primes which are common to all three terms are 3 and a. The smallest power which appears on the 3 in any of the factorizations is 1. We've got a 3 to the first power, a 3 to the first power, and a 3 to the second. So the smallest power of 3 is 1. The smallest power of a is also 1. We've got a to the fourth, a squared, and a to the first power. So the GCF of 9a to the fourth, 6a cubed, 3ab is equal to 3a. So now when we want to factor out the GCF, we write 9a to the fourth as 3a times 3a cubed. We can write 6a cubed as 3a times 2a squared. And we can write 3ab as 3a minus b. Now in each one of these terms, we've got a factor of 3a, 3a, and 3a. Using the distributive property, we can factor that 3a out. We can pull it to the outside, and we are left with 3a times the quantity, 3a cubed, minus 2a squared, minus b. Finally, in our last example, if we want to factor the GCF from the expression 3c times 6c plus 7 minus 2 times 6c plus 7, what we have in this case is the prime factors are not just a single variable, but you have something that's a little more complicated. We've got a prime of 6c plus 7. 6c plus 7 really is a prime because there's no way to express that as a product of smaller polynomials. A smaller polynomial would have to be degree 0. They would have to be a constant. So if we multiply two constants together, we're going to get another constant, not a variable c. So 6c plus 7 is a prime. So if we want to find the GCF of 3c times 6c plus 7 and 2 times 6c plus 7, well, that is simply 6c plus 7. Using the distributive property, we factor that prime out. So we've got a 6c plus 7 times the quantity, 3c minus 2.